Alright, determine the area of the region bounded by y equals 8 over x, y equals 2x, and x equals 4. So the first thing I want you to do on this is graph y equals 8 over x, y equals 2x, and x equals 4. Doesn't have to be exact, just give me a rough sketch so that we can set up the integral. Alright, so we have y equals 8 over x is this line. It's like, if I let x equal 1, y equals 8. If I let x equal 2, y equals 4. X equals 4. Y equals 2, so on and so forth. So I got a little rough sketch there going. Then y equals 2x, that's just a linear equation. Y-intersect is 0, slope of 2. So here's that line. And then x equals 4. So x equals 4, of course, is this line here. Now I want to find the area bounded by these regions here. Okay. So now that we have the rough sketch, let's set up an integral that will give us the area between these two regions, or this shaded region here. So it's going to be the integral of top minus bottom. So that's 2x minus 8 over x dx. Alright, now what are our boundaries? If we have these equations y equals x and we're using top minus bottom, then we need x values. We have this x value here, and we have to figure out what this x value is right here. Now from the graph you can tell what it is, but what if you did a really bad job at sketching those and you couldn't tell? Then you set the two equations equal. So you say 8 over x equals 2x. Then the way that I would solve this is I would cross multiply. So I'll get 2x squared equals 8. Alright, I would divide both sides by 2, and I would get x squared equals 4. So x equals plus or minus 2. Well, we're not concerned. Negative 2 is not even here. It's the only thing it could possibly be is positive 2. Okay, so that's our boundaries. Positive 2 to positive 4. So now integrate this and evaluate. So that's going to be, integrate, you get x squared. What's the integral of 8 over x? It's going to be minus 8 natural log, absolute value of x. Remember, 1 over x is the integral of that is natural log. Alright, so we want to evaluate that from 2 to 4. Alright, so that's going to be 4 squared minus 8 times natural log of 4 minus 2 squared minus 8 times natural log of 2. Alright, so it's going to be, just looking at the whole number part, that's going to be 16 minus 4, that's 12. And then you have a minus 8 natural log of 4. Then you're going to have a what? A plus 8 natural log of 2. And so this would be a problem where you'd want to get a decimal. So you work that out in your scientific calculator. You get about 6.4548. All right, so let's say that we wanted to determine the area of the region bounded by x equals 3 plus y squared, x equals 2 minus y squared, y equals 1, and y equals -2. Alright, so the first thing we need to do generally is to get a sketch of that. Again, it doesn't have to be perfect. Just see if you can give me a rough sketch. So just a couple of points. If you graph those, you may not be used to graphing x equals y, but if x equals y squared is a parabola, it's just, and since it's plus, it's going to be a parabola that's going to be opening to the right. And so you can always take that to the bank. If it's plus y squared, it's opening to the right if you have x equals y. And then, if you can find the x-intercept, which just let y equals 0, you find the x-intercept, then you have that vertex there. You can get your rough sketch going. The same with this. We have a negative in front of this y squared. That means it's going to be opening to the left. If you find the, you can find the x-intercept real quick by just plugging in y equals 0. And you can get this vertex here, get your rough sketch going there. Then y equals 1, you just go to y equals 1, draw a horizontal line, y equals -2, horizontal line. Alright. And so now, once we have all of that drawn, we can see here, this shaded region in here is, that's what we're looking for. We want to find the area of that region. So we say right curve minus left curve. Alright, so let's set up an integral. The integral of, alright, the right curve is 3 plus y squared minus the left curve, 2 minus y squared. Okay? And then, of course, that's dy, because this is all with respect to y. Now we need to figure out the boundaries. Now remember, the boundaries, if you're integrating with respect to y, are the y intersection points here. So it's going to be from y is what? -2 to 1. So -2 to 1. Okay. So I would suggest, and I have had some students in the past, they'll like just start integrating. I mean, if you can do some algebra in here, just some combining like terms, it's going to make your life easier. You don't have to integrate each term separately, because you can say 3 minus 2 and then y squared plus y squared. So you get 1 plus 2y squared dy. Alright, so integrate each one of those separately, and so you get y plus 2/3 y cubed. And we're going to evaluate that from -2 to 1. So first, plug in a 1. So you're going to get 1 plus 2/3 minus, now plug in a -2. So we'll get -2 plus -2 cubed is -8. So that's going to be a negative 16/3. Alright, so this is 5/3. Those two is going to be, those are both negative, so you could just say 2 times 3 is 6 plus 16 is 22. So negative 22/3. And so it's going to be, if these two terms is negative 22/3, you're subtracting them. So it's going to be plus 22/3. 5/3 plus 22/3, that's 27/3, or 9 square units. Okay. So now we're going to take a look at volume. And the volumes that we're going to be looking at, we're going to take curves or graphs of curves, and we're going to take those and revolve them about the x-axis, the y-axis, or a line. And if you revolve something about a line or an axis, then that would make a three-dimensional object, and so that's we can find the volume of that object if we use the right formulas and set up the integral correctly. Okay. Instead of summing up, say, rectangles, if you take that into 3 dimensions, we could sum up discs. And so that's what we're going to work on first. Volume by the disk method. Alright, so we can find the volume of a disk, which, if you think about it, think about different types of disks, like a frisbee. You know, there are lots of applications in the real world. You know, even some peels, funnels, pistons. Your book says, you know, pistons, bottles, things like that have some type of disc shape to them. And when we were looking or just considering the area, I told you we were summing up rectangles. Whether those were vertical rectangles or horizontal rectangles depended on the orientation of the graphs, whether we had y equals x or x equals y. Okay. Now with the rectangle, whenever we were summing these up, we had a height to the rectangles and we had a width to the rectangles. And of course, a rectangle is always going to have a height and a width. But what if we were to take this rectangle and revolve it about, say, this x-axis right here? And so I'm going to kind of turn this axis on its side a little bit. If you were looking at it from the side and you revolved this disk around the x, then it would kind of make a solid figure. You know, it would have some width, so it's pretty hard to draw in 3 dimensions really good without a x, y, and z axis. But just pretend that you were looking at that from the side. And again, like I said, it's pretty hard to draw, right? So there's a pretty good picture in your textbook of what that would look like. kind of like that. You know, you still have that rectangle there, but it's been revolved about some line. This is, I just said the x-axis, but it doesn't have to be the x-axis. And so that would make a disk. And how do you find the volume of a disk? If you know this radius here of the disk, of the outside of the disk, then, and you know the width of the disk, you can find the volume by saying pi times the radius squared times the width. Okay? Remember, the width is what we call delta x. Remember on the, with the rectangles, the width of all the rectangles, we let delta x get smaller and smaller and smaller, and we sum up an infinite number of these. Well, what if we let w, or the width, get smaller and smaller and smaller, and we sum up an infinite number of these disks? Then we can find the volume. Alright, so the volume is equal to pi times this radius here, which I'm going to call capital R, squared, times that change in the width, delta x. All right, so the formula that we use when summing up an infinite number of these disks, of course, is going to be an integral. Okay? And the integral is, for the volume, it's going to be pi times the integral from a to b of that radius, capital R, which is the same as the height of one of those rectangles. But remember, the height of the rectangle is gonna, that height makes that big solid figure. Okay, so it is whatever that radius is squared dx. Okay, so you might be thinking of a radius as a finite number, as some number. So, well, I can, you know, I can get a tape measure and I can measure that radius. Well, if your function, maybe your function's graph looks something like this, or part of the graph looks something like this. Well, we don't want to think about, you know, say that I wanted to find the volume of the graph of f if I looked at just the parts of the graph where x equals 0 to x equals 2. And so if I took this right here, this part of the graph, and I revolved it about the x-axis, and I made a solid figure, you know, it's going to make some funnel type figure whenever it's revolved around. And it's going to be a solid funnel type figure, you know. And so you may be thinking, well, how do I know what the radius is? The radius right here is 0. The radius right here is 2. Well, the radius is changing depending on where you are on this function here. You know, if I'm right here at 0, the radius, there's no radius. It's 0. But if I'm, say, right here, here's the radius, right there. That's the radius that's halfway between here and here. You know, this distance is. Right here, here's the radius. Right here, here's the radius. Right here, here's the radius. So it depends on where you are on this function, whatever that function may be. Let's just call it f of x. And so whatever that function is right there gives us the radius of the big figure that we would get if we revolve this line about the x-axis. And so sometimes figuring out what that radius is the toughest part. A lot of times it is. Alright. Now all the figures, or this, the first figure we looked at, the big disk, and this figure here, these are all solid figures. Okay, and when we have a solid figure, then we can use something called the disk method. It will take and sum up an infinite number of disks by using this formula here. Now I will want to use this formula here if I have a horizontal axis of revolution. So what am I talking about? Horizontal axis of revolution is, what are you revolving this thing about? The picture that I have drawn here, I have this funnel-shaped figure drawn about the x-axis. That's a horizontal line, a line left to right. So as long as I have a horizontal axis of revolution, I'm going to want all of my functions y equals x. I'm going to want to integrate with respect to x, and I'm going to want my boundaries to come from the x-axis. Alright, now if I revolve about a y or a vertical axis of revolution, because it doesn't have to be the y-axis, you can revolve a graph about a line. But if you do have a vertical axis of revolution, then volume is equal to pi times the integral of from C to D r of y, capital R of y squared dy, where this is still the radius. It's just that instead of a horizontal axis of revolution, we have a vertical axis of revolution. So we want all of our equations, our lines that we're looking at, our radii, our big radius here, to be x equals y. So we integrate with respect to y, and these boundaries here, C and D, they come from the y component, or the y-axis if we're revolving about the axis. Alright, so let's think about, again, a horizontal axis of revolution and a vertical axis of revolution, and what that actually looks like. Think about, in your mind, horizontal and vertical. Alright, in 2 dimensions, which we draw all these graphs. Remember, horizontal axis of revolution means you're revolving about some line that's horizontal. You're taking these rectangles, and you're an infinite number of these rectangles, and you're revolving them about a line. And when you revolve them, you're making disks. You're making solid disk figures. The same goes for the vertical axis of revolution. It's just, instead of a vertical rectangle, we're taking a horizontal rectangle and revolving it vertically, which is making a disk around the vertical line. So you see this rectangle right here? If you revolve that around the line here, this vertical line, it makes a solid figure, a disk. Okay? let's find the volume of the solid formed by revolving the region bounded by the graph f of x equals the square root of the sine of x, and the x-axis x is greater than or equal to 0, less than or equal to pi, about the x-axis. Alright, so first let's just sketch what this would look like. Alright, so we're going to let x be values between 0 and pi. So say here's 0 here. I'll let this be pi over 2, and this will be pi. Now you can plug these values in here, in for sine. If you plug in a 0, the sine of 0 is 0. If you plug in a pi over 2, the sine of pi over 2 is 1, the square root of 1 is 1. So let's let this be 1. So that'll be our high point. And then the sine of pi is 0. Now this graph is not V-shaped opening downward. It's a smooth curve. It's a trig function. So this is going up and then coming back down. So that's what that looks like between 0 and pi. That is the square root of the sine of x. Now we want to revolve this about the x-axis. So when we make these vertical rectangles, and again it's an infinite number of these things, and we revolve them about the x-axis, then imagine the type of shape that it would make. It'd kind of be like a football, probably more like a rugby ball or an egg shaped figure. It would, let's see, it looks something like this here. Alright, and so we want to figure out the volume of this shape. So all of those rectangles that are being made, and those rectangles, whenever we revolve them about the x-axis, make discs. This is a solid figure. What is the height of each of these rectangles? The height of the rectangle is going to be the same as the radius of the disc. So look at the heights. They're changing. What's making these change? This shape right here, or this line right here. And what line is that? What line is that right there? That's what we graphed down here. So the radius of each disc is changing according to the function. Alright, so we're going to find the volume of this figure by following the formula. Pi times the integral of Well, what's the radius? The radius is the function. The radius squared dx. We have a horizontal axis of revolution, so we want y equals x. This is the radius, depending on where we are. Now, what are our boundaries on the x? 0 to pi. That's right. All right, so square that. When you square the square root of sine, what do you get? Sine. So we're integrating sine. The integral of sine is negative cosine. There is a pi in front, so you just bring that down. This isn't pi minus cosine. This is pi times negative cosine, evaluated from 0 to pi. So pi times, I'm going to have negative cosine pi minus negative cosine 0. Plugged in pi minus I plugged in 0. Alright, so that's pi times, the cosine of pi is negative 1. So this is the negative of negative 1, which is 1, plus cosine of 0 is 1. So what's my volume? 2 pi. So 2 pi cubic units is my volume. All right, let's look at this problem. So if we take this, the graph here, the part of the graph we have, y equals 4 minus x squared, and we take the area under it and form rectangles, and with those rectangles we revolve them about the x-axis. Then we have a horizontal axis of revolution. Think about the shape that that would make. Okay, so it would kind of be, I guess, like maybe half an egg, or I'm sure you could think of a better, not the, I guess, cut down long ways. You could probably think of a lot better picture. I don't know what exactly that would be. That would be some solid figure. Okay. So since we have a horizontal axis of revolution, then what we need to do is figure out how could we find the radius of each disk that's made. And the radius of the disk is going to depend on what? The function right here. So the volume of the figure would be the integral of, we said the radius is going to be 4 minus x squared, and then you have to square that, right? Because the formula is the radius squared dx. Now we want to use x boundaries. So what are my boundaries for my integral? 0 to 2. Now you need to square that first, so don't just say 4 squared and x squared squared. You have to FOIL that out. Alright, so the volume is going to be equal to the integral from 0 to 2. FOIL that out. After you FOIL that out, you should get x to the 4th minus 8x squared plus 16. So now we can integrate, so that's x to the 5th over 5 minus, that's going to be 8/3 x cubed plus 16x, evaluated from 0 to 2. So Plug in a 2. Oh, wait, what do we have on the outside? Have a pi. Don't forget the pi. Pi is good. Pi, right? So we will have a pi on the outside of that. Alright, so from 0 to 2. So plug in a 2. Pi times 2 to the 5th is 32. And over 5 minus, that's going to be 8. 8 times 8 is 64 over 3. Plus 2 times 16 is 32. Now what do I get when I plug in 0? 0, 0, 0. So you don't have to worry about plugging in the 0 on this one, because you just get 0. Alright, so just get a common denominator and put those numbers together. Common denominator of 15 would probably work. 5 goes into 15 3 times. 3 times 32 is 96. 3 goes into 15 5 times. 5 times 64 is 320. And then 32 times 15 is 480. So 480 minus 320 plus 96 is going to be 256. That's over 15. So my answer, my volume, is 256 pi over 15. Alright, it's cubic units. Alright, so let's look at this problem. Y equals the square root of 16 minus x squared revolved about the y-axis. Okay, so we have the graph here. This is just the positive part of the graph. This is the positive square root of 16 minus x squared. Alright, and so if we take and we revolve that about the y-axis, right, that'll make discs about the y. Alright, and so if we revolve about the y with the shell method, I'm sorry, the disk method, what we're doing now, then we have a vertical axis of revolution. And with a vertical axis of revolution, we want to set up our equation x equals y. And then we want to use the boundaries on the y. From C to D, both of these come from the y. So it's the same formula, except we use y boundaries, and we want the function, this r of y is x. We want it x equals. Alright? So if this is our equation, we need to make that x equals. So how would you do that? Square both sides to get rid of that radical. So you have y squared equals, when you square the square root, you'll have 16 minus x squared, right? So now I want x equals, so if I move this x squared over and I move this y squared over, I'd have x squared equals 16 minus y squared. And then to solve for x, I take the square root of both sides. So I have x equals square root of 16 minus y squared. This is the same as this. You know, the graph is the same. It's just written x equals instead of y equals. Okay, and what is the radius of each one of these discs that's going to be made? It's the height of the rectangle. So the height of the rectangle depends at where you are on this function. You see, the height of the rectangles would change. So that means that the radius of the disk would change. depending on this curve right here. Alright, and this curve is x equals the square root of 16 minus y squared. So our volume equals pi times the integral of the radius of each disk, that's 16 minus y squared, squared dy. Now what are the boundaries? The boundaries are going to come from the y. So here's the bottom of the figure. That's y equals what? 0. Here's the top of the figure. That's y equals 4. Now before I do that integral, I want you to notice something. At y equals 0, what is my radius of the figure? You'd plug in a 0. It's the square root of 16, or 4, just like the graph looks. It does work. It's 4. Alright, what is the radius of the disk when y equals 4? Now think about this being revolved. There is no radius. So if I plug in a 4, I better get 0 for the radius. I said this was the radius here. That's what I plugged in. What if I plug in a 4 right here? You get 0. So what I'm plugging in does represent the radius. Okay? It's just trying to help you understand what's actually going on. Anytime, whatever you write in the formula right here, this radius, you can check that by just plugging in whatever values you have on your sketch or your graph. Alright, so square that. So I have pi times the integral from 0 to 4 of 16 minus y squared dy. Right, when I square that, you get rid of the radical. So it's going to be 16y minus y cubed over 3. I'm going to take that. You say pi times that, evaluated from 0 to 4. When I plug in a 4, 4 times 16 is 64. And then minus 64 over 3. When you cube 4, you get 64 over 3. And then when you plug in a 0, you get 0 and 0. Alright, so whatever I get when I say 64 minus 64 over 3 is going to be my answer. So I got pi times 128 over 3. Or 128 pi over 3 cubic units. Alright, so let's say that I have the function f of x equals 2 minus x squared. And I have the line g of x equals 1. And I want to take the region that's bounded by those two graphs, take the region bounded by these two graphs, and I want to revolve that region about, so I'm going to revolve about y equals 1. Alright, so you are going to need to be able to sketch lines. So you need to be able to sketch f of x equals 2 minus x squared, just a rough sketch. G of x equals 1, so it's like y equals 1. And then we're actually revolving it about y equals 1. Okay? And so if you do that, you're going to get a graph that kind of looks like this. Okay? So this line right here, that's 2 minus x squared. Of course, your graph would probably come on down, and that's okay. This line right here from left to right, this is g of x equals 1 or y equals 1. Same thing. Now, I'm going to do my own rough sketch here because I want to look at something. So you probably had a graph kind of like that. You'd have a graph kind of like that, where this is y equals 1. And we're taking this right here, all of this stuff between these two, this region, and we're revolving it about the line y equals 1. Now that's different from revolving about the axis, because why? Well, whenever I make these rectangles, you don't actually have to make them. We're doing the integral that's summing up all of these. But if I make this rectangle right here and revolve it about this line, y equals 1, think about the shape that would be formed. It'd be kind of egg-shaped, a little bit. If I was to take, you can look at this prettier graph here. If I was to take this and revolve it about this line, imagine a mirror on the bottom of this and it in 3 dimensions. Okay, it would look something like this here. Okay, and so think about the function we have here. If I plug, let's just say I plug x equals 0 into this function right here. Right here. Here's the function, and I plug in x equals 0. Is the height of the rectangle right here going to be what I get out when I plug in x equals 0? Look at your graph. When you plug in x equals 0 into this function, you get 2. But is this height 2? No, it's not. Why is it not? Because we're revolving about the line y equals 1, so my rectangle is stopping right here. Now, if I was talking about this rectangle here, all the way down, then its height would be 2. But I'm not talking about that because I'm not revolving about the x-axis. I'm revolving about the line y equals 1. So my rectangles are going to be between y equals 1 and wherever I am on this graph. You see my rectangles, the heights are changing? And so as I'm revolving all of these rectangles, an infinite number of them, you see my height changing, changing with the function. But if I plug a number into the function, I'm getting the height from the x-axis. That's what it gives me from the x-axis up. Alright, so how can I adjust for that? You take the function and you subtract 1. Well, you say, why are you subtracting 1? Well, remember when we were doing the area between two curves? How did we find that distance? Top minus bottom. That's what we're doing here to find the radius of the disk we would have. Top curve minus bottom curve. Top curve minus bottom curve. That will give us the height of the disk, or the radius of the disk. Okay? So, to find the volume, that's going to be equal to pi times the integral. Now, what are our x values? We have to figure those out. Wherever this intersection points are, here and here, that's going to be the boundaries of our graph. And you know how to find intersection points. You set the two graphs equal. So if I say 2 minus x squared equals 1, this is how I find the intersection points of the graph. So what is x squared? X squared equals 1. So what is x equal to? Take the square root of both sides, plus or minus 1. So negative 1, positive 1. Alright. How do we get the height of each, or the radius of each disk? Top minus bottom. So top curve minus bottom curve. Top minus bottom gives us the radius. So that's 2 minus x squared minus 1. This is a horizontal axis of revolution, so we want y equals x. So this is dx. 2 minus x squared minus 1 is 1 minus x squared. So that's what I'm integrating. Now, what did I not put here? Squared. Don't forget that's from the formula. Squared. It's the radius of the disk squared. So square that. FOIL it out. That's going to be 1 minus 2x squared plus x to the 4th. So that's pi times x minus 2/3 x cubed plus x to the 5th over 5, evaluated from -1 to 1. So that's x times, alright, plug in a 1. We're going to have 1 minus 2/3 plus 1/5 minus, plug in a -1. We're going to have -1 plus 2/3 minus 1/5. Work all of that out, and you're going to get 16 pi over 15, or 16/15 pi. Okay. So if you ever revolve about a line, you need to be careful if that line is not the x-axis or y-axis. Because you know the height of each disk that's going to be made is not dependent on just this top curve. If it was, like I said, you would be making rectangles all the way down to the x-axis, but you're not. You're just taking this figure and revolving it about y equals 1. So I mean, it's going to make just a mirror of the other side. It's going to be that figure, that egg-shaped figure, lemon-shaped figure, I guess, something like that. All right. Now, what if I was to take look up here real quick. Let's say that I had this graph, this part of this graph here, and a part of another graph here, and let's just call one of these F and one of these G, and I took this here and revolved it about a line or an axis. So think about it. Think about if I had this here, this, I guess, kind of banana shaped deal here, and I took it and I revolved it about the x-axis. I have the most slanted axis in the world. Let's see. Alright, let's just pretend that's good, even though it's not. So then, you know, if you made a mirror of that on the other side, kinda, oh man, that's really bad. So something like that. Then do you see it's not going to be a solid figure, at least if my drawing is not that great. At least you can hopefully see it's not going to be, and oh yeah, that's looking a lot better now. It's not going to be a solid figure. It's going to be kind of a funnel, but it's going to get, you know, it's going to be thick around here, but it's still going to be missing stuff all the way down. Okay, so got a little better picture of it right here for you. Alright, and so you can see it's missing stuff in here. Alright, well, we're still making little discs by taking small rectangles and revolving them about this, but we have to be able to subtract this inside out of the volume. If I was just talking about this outer line right here and I revolve that, then that would make a solid figure. But since I had just this piece and I was revolving that, there's going to be a lot missing in here. So if I take the outer radius, which I'm going to call capital R of X, which is the same height or radius that I had before, and I subtract the inner radius, then that will give me the volume of the figure. But the way the formula works, you have to say the outer radius squared minus, they call the inner radius lowercase r of x squared. Okay. So the formula is the pi times the integral of the outer radius squared minus the inner radius squared. This minus the inner radius squared, what that's doing is that's subtracting all of this stuff in here that that you don't want, or that's not in the figure. So here's what's happening. I'm gonna draw something up here. I just don't want it to confuse you too bad. So you're taking this rectangle here and you're revolving it about the axis and you're getting the solid figure. Then what's happening is you're taking this rectangle here and revolving that about the axis or about the line, and you're subtracting that away. So you're subtracting the volume of all the missing stuff. This is the volume of the solid figure. This is the volume of all of the hollow part. And that gives you the volume of the entire figure. I mean, that's in real layman's terms. That's as easy as I can break that down. You're taking the volume of the whole thing and then you're subtracting that inside that's missing. But the way the formula works, you have to say the outer radius squared minus the inner radius squared. This is called the washer method. Everyone knows what a washer is, right? There's all different types. If you have put together swing sets or, you know, dealt with water hoses or whatever, washers are everywhere. Put together an exercise bike, you know, anything, you're going to have washers usually in your construction. And so washer's kind of a donut hole shaped figure. And again, there's all kinds of shapes and sizes. But if I was to take, instead of having, I had a whole rectangle and I revolve that about the x-axis and I make a disc. Well, what if I just have this piece right here and I'll revolve it about the x-axis? This little part that I'm missing in here, when I revolve that, that's going to leave a hole. So that's where the washer comes in. So the distance from the center of the figure to to the top, that's the capital R of X. And of course it depends on where you are as to where the top is. The distance here in the center to the top of the missing part, that's the lowercase r of X. So if you find the volume of the whole thing and then you subtract out the missing part, then you have the volume of the figure. All right. That's called the washer method. When you're missing something inside, you have to use the washer method. All right, so let's say that we want to find the volume of the solid formed by revolving the region bounded by the graphs of y equals the square root of x and y equals x squared about the x-axis. So the first thing I want you to do is sketch those two graphs. Just give me a rough sketch of them. Alright. So this top curve here, that is y equals the square root of x. This bottom curve here, this is the piece of y equals x squared that we're going to use. Now your graph, you probably extended on out here and you probably have it extended on the other side here, and that's okay. We're just worried about the region that's bound here. So the region that's bound here is between here and here. If we revolve that about the x-axis, that is a horizontal axis of revolution, then you can see how this figure is shaded a little bit. Kind of makes it look like it has a hollow inside, at least, for the most part. Now, I wouldn't exactly call that like bowl shape, but there could be a piece on a machine that could look like that. So let's say that we had this piece and we revolved it about the x-axis. And we want to know what would that volume be of the figure, Then the way we can get that is we can say that volume is equal to pi times the integral of, we need to say the outer radius minus the inner radius. The outer radius is going to be from this line all the way to the x-axis. So the outside of this figure, you would get that distance from this function here, y equals the square root of x. So it's the square root of x squared minus the inner radius. Which graph would give us the distance from here to here, the inside that we're missing, the inner radius, that would come from this graph, which is y equals x squared. So it's minus x squared squared. Do not forget that you have to square the outer radius and the inner radius in the formula. Now, the intersection points, since this is a horizontal axis of revolution, the intersection points are going to come from the x-axis. They're x values. This is dx. So how would you find them? Looking at the picture? No, we don't want to find them that way. Set the two functions equal to find the intersection points. So, well, right above it here, square root of x equals x squared. Ooh, how do I solve that? Square both sides to get rid of that radical. So that's x equals x to the fourth. Alright? Set everything equal to 0 and solve for x by using the zero product principle. So if I move this x over, I have x to the fourth minus x equals 0. How do I solve that? By factoring. Factor an x out, I'll have x times x cubed minus 1 equals 0. Set each factor equal to 0. So I have x equals 0 and x cubed equals what? How do you solve x cubed equals 1? Take the cube root of both sides. So x equals 1, x equals 0. That's the two solutions. Well, look here. X equals 0 is right here. X equals 1 is right here. That's my boundaries. 0 to 1. Alright, so I have pi times the integral from 0 to 1 of, square that, you get x. Square that, you get x to the fourth. Now integrate each. X squared over 2 minus x to the fifth over 5. Evaluated from 0 to 1. So this is pi times, that's going to be 1/2 minus 1/5 minus, what do you get when you plug in a 0? 0. So 1/2 minus 1/5, that's going to be 5/10 minus 2/10, 3/10. So that's 3/10 times pi. That's the volume. Let's take a look at this problem. Find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the given lines. Now we've mainly been doing just about the x-axis or about the y-axis. So I'm confident that you could do okay in setting up the integrals and getting those answers. Just be careful, you know, if you revolve about the x-axis and you're using the disk method, you need to make sure that you have y equals x, which you do. If you're revolving about the y-axis, which is a vertical axis of revolution, then you need to have x equals y. So solve for x here. Alright, so be careful there. Now, C and D are going to be a little different. I'm just going to randomly choose one. I'm going to choose the last one because it's vertical. And so I'll need the same orientation for x equals 2, about the line x equals 2, as I would the y-axis. Because remember, x equals 2 is a vertical line. So I'm just going to do a real rough sketch. It doesn't take a perfect graph to get these right. Y equals 2x squared is one of these functions. You know, that could be y equals 2x squared or y equals x squared. For our purposes, though, it's good enough. The line y equals 0, see if I can get a different color out here. Y equals 0 is going to be this line here, the x-axis. And x equals 2. So 1, 2. So this line right here is x equals 2. Alright, so the bounded region is going to be this stuff in here. Alright, now I want to revolve the bounded region, this in here, about the line x equals 2. This is the line x equals 2. Now, since I have a vertical axis of revolution, I need x equals y. So this equation right here needs to be x equals y. So solve for x. First, you would divide both sides by what? 2. So you'd have x squared equals y over 2. Then take the square root of both sides. So x equals the square root of y over 2. Alright. Now, here's what we need to make sure. We need to make sure whenever, is this, first of all, figure out, is it a solid figure or is it going to be missing stuff? It looks pretty solid to me. When you revolve this about that line, there's no space anywhere. So you're going to have a solid figure. Alright. So it's not, we don't have to worry about an outer radius and an inner radius. Or the inner radius is simply going to be 0, if you want to think about it like that. We need to figure out how can we get this distance. And look what I'm going to draw up here. We want the distance from here to here, here to here, here to here, here to here, because all of those are going to be the radii. Each one of those is a radius of the disk that I'm going to make when I revolve about that line. Now I can draw the other side of that line up there if that helps you kind of visualize it. You know, it's gonna come down and look like that. So it's gonna be kind of like an upside down, or maybe like a volcano with a tip on the end, or an upside down tornado, if you want to think about it like that. That's going to be the figure. All right, it's going to be solid. We just want to make sure that the radius we write down will give us the distance from here to here, or here to here, here to here, here to here. Now, the thing that helps me the most, and wake up if you're not awake, because here's what helps me the most when setting up these problems, because you can't always just use a function and say, oh, it's going to be the function, you know, and it not work out because you didn't write down the radius right. We need to figure out whatever we have for our function at this place right here. What is this distance? Just, you know for sure, without a shadow of a doubt, if this line is x equals 2, whatever radius I come up with here, when x equals, when y equals 0, we want this to equal 2. This is y equals 0, right? It's x equals 0 too. But as far as we're concerned with this problem, we want this radius, or this distance right here, when y equals 0, x equals 2. Now look up here at the very top. What do you think the distance between the left side and the right side is at the very top? there's not a distance at all. It's 0. The radius. I'm still thinking about that radius of the disk. Maybe I wasn't clear there. The radius of the disk up here is going to be 0. Radius equals 0, right there. Radius right here, I know I drew the arrow down here, but the radius of this disk, which I just erased by making it blue, but it's still, you know, the radius of this disk is equal to 2. So whatever I come up with as a function, I know 2 test points I can take. If I know what this x value is right here, or this y value is right here, I can figure out and make sure whatever I've come up with gives me a distance or a radius of 0 right here. And whatever radius I come up with will also give me a radius of 2 right here. Alright. So, if I was just to look at this function up here that I have, x equals the square root of y over 2, that's this line right here. This line is x equals the square root of y over 2. Is it not? Hopefully you understand that. This line right here, actually this whole parabola here could be thought of as x equals plus or minus the square root of y over 2. But for what we're using it for, we're just concerned about this right here, because that's got to have something to do with it. Okay. Now if I just chose this, I'm just going to write it down. If I just chose this as my radius, my outer radius, then when y equals 0, what would my radius be equal to here? If y equals 0. You say, why are you choosing 0? Because on this graph right here, I'm looking at when y is 0. What is my radius? 0. What should it be? It should be 2. Okay? Now, what's the y up here? How can I figure that out? How can I figure out what this y value is? If you set this equation and this equation equal, then you'll get what the height is. Or, I'm sorry, you'll get the intersection point here. Like, since I know this is x equals 2, and I know this is what? Square root of y over 2. So if I say 2 equals square root of y over 2 and I solve, square both sides, that's 4 equals y over 2. What's y equal to? 8. So this up here is the line y equals 8. Alright? Now, when y equals 8, what does the radius of the disk need to be? 0. When y equals 8, the radius of the disk needs to be 0. When y equals 0, the radius of the disk needs to be 2. That's our 2 test points that we can use to make sure we're setting up our equation right. Well, look up here. If we plugged in a 0, we get a 0. So that's not right. It needs to be 2. When we plug in an 8, what do we get? 8 divided by 2 is 4. The square root of 4 is 2. So it's kind of like we're just getting the opposite of what we need. So instead of the square root of y over 2, what if I was to make this, watch what I do now, 2 minus the square root of y over 2? You say, where did this 2 come from? Well, think about it. Down here, I want a radius of 2. when I plug in y equals 0, which is right here on this graph, what y would equal, then I would have 2 minus 0. So that would give me 2. That would give me a radius of 2. Then, what if I was to look up here where y equals 8? I want to get a radius of 0 for that disk. So if I plug in an 8, 8 divided by 2 is 4, square root of 4 is 2, 2 minus 2 is 0. So this right here, this is the formula that I need to use for the radius. Now, volume equals pi times the integral of, this is my radius, 2 minus square root of y over 2 squared dy. Now what are my boundaries? My boundaries, since I have x equals y, you know, I have r of x here that is actually r of y, but it's really just x equals this. So don't let that confuse you though. But what are my boundaries? They need to come from the y. 0 and 8. Alright, so now I want you to try to integrate this. What do I have to do right here? Square that. So you need to full that out. Okay?